How do we form a solution? How to make a solution. It's just how chemists solve problems. They create solutions. Ha 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 ha. Or that is so funny, like helium. He 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 he. So let's just give you some examples of what I'm talking about when I mean solutions. Okay, so we can have gas in a gas. We can have gas in a liquid. We can have a liquid in a liquid. We can have a solid in a liquid. This is what students think mostly solutions are. We could have a liquid in a solid, and we could have a solid in a solid. So by looking at the chart, I've given you some examples of these different types of solutions. Solvent is the important one because you can see that there's a lot of water on here, and that's because water is polar. It makes it a great universal solvent. It likes to dissolve lots of other things. And when you look at these solutes, for the most part, a lot of times students like to think that they're more of a solid. But oxygen is a gas, and it can dissolve into nitrogen, and that's really how our air is that most gases are dissolved into nitrogen gases surrounding it, and that's actually our atmosphere. But by looking at some other things like carbonated water, I mean, that's a gas, carbon dioxide dissolved in water. And antifreeze, believe it or not, that's ethyl glycol, and it's dissolved into water. And solid into a liquid, that's usually an example that we use about a solution, for younger students too, that we're taking a salt, which is a solid, usually sodium chloride, but there's lots of different types of salts, and we're dissolving it in water. And then mercury, we can dissolve that in silver. That's physically putting the liquid dissolving into a solid. We use that in making tooth fillings and such. And then a solid into a solid. So in order to get carbon to dissolve into, which is a solid on the periodic table, its natural state, to get it to dissolve into another solid iron, that creates a solution of steel. So the formation of these solutions, it can be exothermic or endothermic. It depends upon the relative strengths of those intramolecular forces and particle attractions that happen. And this is usually, affecting the dissolution process, or that's the fancy term for dissolving process. But you can see if I put this as a salt illustration with water. Water is, it's got that partial positive and partial negative side, and when the salt hits the water, the partial positives, all right, are going to find the negative chlorine ions and kind of surround it, and the partial negative side, which is the oxygen, is going to find the sodium ions and surround it, and that's how we get dissolving. There's a step in the formation of how a solution happens. First of all, you have to have a solvent and then a solute, right? So what's dissolving in the solute? And then you have to have these expansion of these particles, because in order for them to interact, they have to expand. We have to break the intermolecular forces that are contained within the solvent and the solute to create room and opportunity for them to bump into each other and create the solution. All of this takes time, and the next video series, I think, is the factors that can affect this, slowing it down or speeding it up. But essentially, the solute will have to disperse for the most part, and it's going to disperse from a higher concentration to a lower concentration until it reaches equilibrium. So something is soluble if it has the ability of a solute to dissolve in that solvent, and it forms this homogeneous. Homogeneous means it's the same, throughout it. It's insoluble if the solute does not dissolve in a solvent and not form this homogeneous solution. It kind of tends to stick around by itself, not dispersing evenly like like when something is soluble. So not everything is soluble. It's not going to come apart and interact with the solvent itself. Generally, when ionic compounds are dissolved in water, the components of the ions, they're separated and then they're dispersed. And the presence of these can, be detected by a conductivity meter. Learned about this in bonding, where if I have something like sodium chloride that's ionically bonded together, that has a positive sodium ion and a negative chlorine ion, and when we put that into water, it comes apart and it's sodium plus ion and it's chlorine -1 ion. And that can actually conduct electricity, working similar to a battery, creating a positive part and a negative part. And so it can create a conductivity, something that we can actually measure. So if you look in the diagram here, we have electrodes hooked up to different solutions, and then on the other end over here, there's a battery, right, component. And so if the water will conduct electricity through its electrodes, the light bulb will light up. So even if there's just a few ions, like tap water, the light bulb will light up. The positive and negative ions are creating this bridge for the electrical current to carry, creating a conductivity that is measurable. And the more ions that we have, you can see the brighter this light bulb is, the brighter it's going to get with the more ions that dissolve, or the higher concentration of ions that are dissolved inside of the water. This guy over here, he's not lit up at all, so there's no ions dissolved in this. This would be something like deionized water. In order to make a solution, we have to first determine how much grams that we're going to need. And then we want to dissolve a solute in a small amount of solvent. So once we weigh the solute and we get our solvent, let's say it's going to be water, we want to dissolve a small amount into it. And we're going to transfer it to, this is called a volumetric flask. These are these long, skinny glassware types that are shaped like this. And then once that happens, we're going to add distilled water, right? Pure water, because we don't want other ions interacting with what we're trying to make. And carefully shake the actual container. And then these volumetric flasks, they actually have a little line that's etched in here. That's why they're so expensive. Every time one of them is manufactured, they're made, most of them are to 1,000 milliliters, but there's different sizes. And we pay somebody, or the company pays somebody to etch this like 1,000 milliliter line in there. And so once all of it is dissolved, then we drop by drop add water until we get to actually this line. We have to make sure that whatever other container that we use, that we rinse out the whole solution. Rinse out the whole solution that's in our mixing container. And so I love this diagram because this shows you how to make a solution. The example in this problem is we're going to make a 200 liter solution of a 0.7 molar sodium chloride solution. So first of all, we have to find out how much solid that we're going to need, and we use the calculation of molarity to figure that out. And it says that we're going to need 91.17 grams of sodium chloride, and it looks like we are making a 200 liter solution. So we're going to measure out into the balance using a weigh boat and measure out to 91.17 grams of salt. And then we're going to pour it into that volumetric flask and just add enough water to kind of get it to dissolve thoroughly, and then mix and swirl. You always want to put a stopper on it, because if it spills out, you got to start all over again. And then we want to add enough water to just come up to that etched line that I talked about. That's a calibrated line. If you've ever measured liquids before, like especially in a graduated cylinder, you know the graduated cylinder is kind of like this, and there's little lines. And any sort of liquid is going to do this cohesion and adhesion property where it forms meniscus, and we always want to measure like at the bottom of that meniscus. And so in the drawing you can see here that we're measuring at the very bottom of the meniscus.